In engineering drawing, if you want to solve any question on lines, we need to first understand the master solution. Now what this master solution is and how we are to draw it, we will be watching in this video a little later. Let's first of all revise some basic concepts that we have learned in our previous videos. Now we all know what a quadrant system is. The first, the second, the third and the fourth quadrant. If a point lies in the first quadrant, then its front view, which falls on the vertical plane, will be above the xy line, and its top view, which falls on the horizontal plane, will be below the xy line. In the second quadrant, both the planes, the HP and the VP, are above the xy line. That's why the front and the top views both will be above the xy line. In the third quadrant, the horizontal plane is above the xy line. That's why the top view goes above the xy line and the vertical plane is below the xy line. Hence, the front view will go below the xy line. And likewise, for the fourth quadrant, both the planes are below the xy line. That's why the front and the top view will be below the xy line. Now, all this quadrant system I have explained in a very detailed manner in my previous video. Make sure that you go and watch that video as well. Let's come back to our master solution. Now, if I want to start with the diagram for a line, I need to have 11 different data. Out of them, at least 5 must be known to me. Now, which are those 11 data? We will be looking at them as we keep on proceeding in our solution. Now, what these 5 data that we need to know are: the first one, let us say if I want to draw a line AB. So I have taken this as my line AB. This is endpoint A and this is the endpoint B of the line. Now, to start with the diagram, I need to have the position of at least one of the endpoints of the line AB. Let us say for this, the endpoint A, I have taken the example where endpoint A is taken 20 mm above HP and 15 mm in front of the VP. That means this line has endpoint A, which is 20 mm above the HP and 15 mm in front of the VP. Now people, remember, the master solution is applicable for the points wherever they lie, whichever quadrant they lie. It is applicable for all of them. But for simplicity purpose, what we will be doing is we are going to take this entire line in the first quadrant. So point A and point B, both of them are going to lie in the first quadrant. But as I said, this solution can be extended for points which are lying in any quadrants. They be it in the second quadrant or in the third or in the fourth quadrant. Even if the line, some part is lying in the first quadrant and some part is lying in some different quadrant, still the master solution is applicable. So you don't have to worry about how the problem has to be solved. Just do your master solution very properly, very thoroughly. Let's begin with the solution one more time. So there is endpoint A, which is 20 mm above the HP and 15 mm in front of the VP. So what I'm doing here is I'm keeping this line exactly parallel to the HP. There is a HP over here and there is a VP over here. So this line is kept parallel to the HP as well as to the VP. So there is a HP here, there is a VP here. Now you must be remembering that when you watch the horizontal plane in the front view, the horizontal plane in the front view will be seen like an XY line. So this line and the XY line, the HP, are right now parallel to each other. Similarly, when you go to the top view, when you watch this line from the top, the vertical plane that you have here will be seen like the XY line, and the line is parallel to the vertical plane. That means the line is parallel to the XY line. This point A is kept 20 mm above HP and 15 mm in front of the VP. That's my first data that I will need. So what I'll do here is I'm going to draw the diagram for this particular case. Now I'm going to break this solution into 3 different parts. So I'm beginning with the first part over here. So what I'll do, I'll get the XY line. Then it is told to me that the endpoint A is 20 mm above HP. I know in the first quadrant, the front view will be seen above the XY line and the top view will be seen below the XY line. So this is my 20 mm length. This is say 15 mm length. mark the points. In front view, we will name A dash, and in the top view, we are going to name it as A. So this distance of the point A dash from the XY line, that is the horizontal plane, is 20 mm, and the same distance of the point A from the XY line, that is a vertical plane, is 15 mm. So that's my location of point A. Now whatever happens, the end point A is not going to change its position. So end point A is fixed. The next data that I'll need is the true length of this line. So I will need what is the length of this line. So that's my second data. I have assumed for simplicity purpose again the true length of the line as 100 mm. So this line is of length 100 mm. So far I have given you three number of data. I have given you the position of the endpoint A, how much above, how much in front, that's two number of data. I have given you what is the true length of this line, that was 100 mm, that's three number of data. Now I'll be giving you two more data. The first one is the inclination of this line with the horizontal plane. So there's a horizontal plane and that's your line. Right now the line and the horizontal plane are both parallel to each other. That means the angle between them is 0 degrees. If I tell you that this line is inclined to the HP by an amount of 35 degrees. So there's a HP, there's your line, front view you are observing the HP as the XY line. So HP is seen like the XY line. This is our original line. The inclination between them is say 35 degrees. So this is called the true inclination of the line. So when you are watching this line in the front, this has been inclined to the HP by an angle of 35 degrees, but the line is still kept parallel with the VP. So in the front view, you are still able to see its true length. So that's my stage 1. So I'm going to draw my line which is inclined to the HP by 35 degrees, and you know when you watch something in the front view, it will be in the vertical plane, and the front view, the horizontal plane is nothing but the XY line. So let's make an inclination of 35 degrees. I'm going to name this point, the other end point, as B1 dash. Now the naming is very important. You have to memorize the entire master solution, including the names as well. This is my first stage, that's why B1 has come. The point is in the front view, that's why B1 dash has come. So that's my true length of 100 mm. So this is the line. Endpoint A is fixed at 20 mm above HP and 15 mm in front of the VP. Fix the point A and start inclining it with the horizontal plane with an angle of 35 degrees such that the line is still parallel to the VP. Now, the same line, it has been inclined to the HP by 35 degrees, is now watched from the top. When you watch it from the top, this point A will have its projection down, this point B will have its projection down, and I will be able to see its top view. Now you can understand, when you watch the same line from the top, you won't be able to see its actual length. The length has got shortened. This length is called as the apparent length of the line, and if you bring this B1 down, you are going to get point B1. So that's B1 dash, you bring it down, you got B1. So this B1 is the apparent length of the line, it is not the true length of the line. So this length, since it is observed from the top, it is named as plan length. Short form is PL. So people, I have given you position of the endpoint. Endpoint A, 20 mm above HP, 15 mm in front of the VP. That's 2 number of data. I have given you the true length of the line. That's 3 number of data. I have given the inclination of the line, the true inclination of the line with the HP. That's 4 number of data. I have given you the true inclination of the line with the VP. That's 50 degrees. So we'll come to that a little later. So now the new concept has come here called as the plan length. That becomes one of the data of the 11 data in the list. So that's plan length now. So this is the plan length PL. There is no need to measure what the plan length is. In some of the questions, you might be given what the plan length is. Now, let's move ahead. So that's my stage 1. Stage 1 is complete. So in stage 1, what I simply did, take the line, keep it parallel to the HP, keep it parallel to the VP, fix the endpoint A, incline it with the HP by an angle of 35 degrees, draw its top view. The top view is called as a plan length. The stage 1 is complete. Now let's begin with the stage 2. Again take the line, keep it parallel to HP, keep it parallel to VP, take the endpoint A, 20 mm above the HP, 15 mm in front of the VP, and this time keeping endpoint A fixed and watch from the top. Keeping endpoint A fixed, let's incline this line with the vertical plane by an angle of 50 degrees. Now you remember, when you watch the vertical plane from the top, the vertical plane from the top, the vertical plane is seen like the XY line. This is your original line. It has been inclined to the vertical plane by an angle of 50 degrees. So now let's come in the top view, that is point A. You draw a line which is inclined by an angle of 50 degrees. So I can now say that this angle is phi, which is 50 degrees. I have started my stage 2. So this point will be named as B2. This is my true length of 100 mm. So that's my stage 2. Now this line has been inclined to the VP by an angle of 50 degrees. Let's watch the same line from the front. Now when you watch from the front, this endpoint A will have its projection back here. This endpoint B will have its position back here. That means you now will be able to see only the apparent length in the front view. So the length of this line has been shortened in the front view. So let's draw the front view also. So what I'll do here is I'll project B2 now in the upward direction. So B2 is projected up and you will come and meet with A dash. So this point will be called as B2 dash, and this is now named as elevated length EL. That's your next data. So elevated length EL becomes one of the 11 data. So we have the position, we have the true length, we have the inclination, we have the plan length, we have the inclination with the VP, and now we have got the elevated length. So elevated length is basically the apparent length when watched in the front view. So elevated length EL. Now the next concept that you want to understand is the last stage of the problem. So in the last stage, what we'll do here, I'm going to draw something called as locus of B dash, and then I'll draw something called as locus of B. Now you just have to understand this, how it is drawn. The explanation is very much in detail over here. So if I start explaining all these things, it will become a very long video. So what you need to know is how to draw the master solution. So what we'll do here is, from this B1 dash, I have drawn a line called as locus of B dash. From the point B2, I have drawn a line called as locus of B. Now to get the final view, what you simply need to do is rotate A dash B2 dash towards the locus of B dash. Rotate A dash B2 dash towards the locus of B dash. This point that you have got, which is the intersection of the rotation and the locus of B dash, is called B dash. Similarly, what you now further do is rotate the plan length PL so that it comes and intersects to the locus of B. Rotate plan length A B1 so that it comes and intersects locus of B. So this point is called as B. If you want to cross check whether your solution is correct or not, this point B and the point B dash, both of them have to come in the same line. Mark my words very carefully. If you want to cross check that your solution is correct or not, you have to get these points B and B dash in the exact same line. So understand what I did in the third stage. I simply rotated the elevated length and the plan lengths towards the locus of B dash and the locus of B. I've got point B dash, I've got point B, and the more important thing is these points B and B dash has to come in the same line. Then this A dash B dash line, whose length is exactly same as the elevated length, becomes the front view of the line, and the inclination that has been made by A dash B dash with the horizontal line or the XY line is called its apparent inclination, denoted by alpha. See, you have got a new data. The inclination of the front view with the horizontal or the XY line is called as alpha, the apparent inclination. Similarly, if you join A with B, that will become your top view. This then top view is exactly equal to the plan length, because we have rotated plan length to intersect the locus of B. So that's your top view, and the inclination made by the top view with the horizontal line or the XY line is called its apparent inclination beta. That's your next data. So that means if you observe, I have given you position of the point A, the end point A. I have given you the true length of the line. I have given you inclination of the line with the HP, then the plan length, then the true inclination with the VP, that is phi. Then we have seen the elevated length. Now we have seen how it was rotated. We have got the front view, we have got the top view, and the inclinations of the front view and the top view with the XY line or the horizontal line is called as the apparent inclinations, denoted by alpha and beta. This locus of B dash and locus of B is nothing but the position of point B with respect to the horizontal plane and the vertical plane. That can also be one of the data. So two more data I have put up here. Locus of B dash will give us the position of B with respect to horizontal plane, and the locus of B will give us the position of the point B with respect to the vertical plane. So that's two more data. And finally, once you are made with the front view and the top view, as I've already told you that B and B dash have to come in the same lines. A and A dash were already in the same lines. The final thing that I can do here is extend A and A dash, extend B and B dash, and then measure this distance, which is called the distance between the end projectors, denoted by DBEP, distance between the end projectors. So that is how the stage 3 ends. As I have already told you that this master solution broken into the 3 stages. In the first stage I have drawn the front view, in the second stage I have drawn the top view, and in the third stage what I have done is I have merged the two diagrams together. So if you know the master solution very properly, you can solve any particular question on lines. I hope you have understood how the solution was drawn over here. Make sure that you practice this solution as many number of times as you can. I wish you all the very best. Thank you very much.